Hello, Konstantinos. Good morning. Yep.
Good morning. How are you?
Good morning in Boston. Good afternoon in Athens.
Good afternoon.
It's a really great honor to have you with us. So, on behalf of the organizing and the scientific committee, University of Athens, University of West Attica that host us here, the National Technical University of Athens, and HETIA, the organizer, we are very, very excited to have you with us today. So it's really an honor. It's an early, a fresh conference that tries to bridge industry and academia. And we are grateful for your interest to support the Greek engineering community. Thank you very much. So if you allow me just to say a few words for our guest. So Konstantinos DASKALAKIS is the Avanessians Professor of Computer Science at MIT. He works on algorithms, machine learning, game theory, and statistics. He has resolved long-standing open problems about the computational complexity of Nash equilibrium and the mathematical structure and computational complexity of auctions. His current work focuses on multi-agent learning, high-dimensional statistics, and causal inference. He has been honored with several top honors in his fields of research, including the Nevalina Prize, which is awarded together with the Fields Medal by the International Mathematical Union for outstanding contributions to mathematical aspects of information sciences. Other prestigious honors include the ACM Doctoral Dissertation Awards, the Kalai Prize from the Game Theory Society, the Simons Foundation Investigation Award, and the ACM Grace Murray Hopper Award. He is an ACM Fellow, holds an honorary doctorate from the University of Patras and a honorary professorship from the University of Piraeus, and was awarded the Golden Cross of the Order of the Redeemer by the Greek presidency. He chairs AI Strategy Committee for Greece for the Greek Prime Minister. So that is a very as short as I could. And of course, he's an academic that inspires all of us. We have many students here that came to watch your presentations. And thank you very much for coming to our conference. So the floor is yours.
All right, thank you very much, Barry. It is a great pleasure to be with you, I mean, at least online. I'm sorry to miss the conference. It sounds extremely interesting. And at a personal level, since I haven't been in Greece in a while because of family reasons, I also missed our annual, discussions, that I hold with Paris every summer. In any event,
next year.
Next year, I wanted to talk to you about what I think the world will look like when AI is widely deployed, and what we need to do to get ready for that future. Of course, AI over the past decade or so has penetrated full technological computational stack, from edge devices all the way to data centers, both in terms of how these devices operate, as well as the types of computations that happen inside them. It also has affected various sectors of the technology, and this is an ongoing progress. Every year, this table looks different, and I presume you have some interesting ideas for how to influence how AI is deployed in the economy and the society. So one thing is clear that as AI is increasingly deployed in the real world, we need two things. One, of course, is to make each individual AI stronger or better, which means you want it to be more intelligent in whatever measure of intelligence you have defined. But also you want to make it more data efficient, compute efficient, and energy efficient. As you know, this technology is very data hungry and compute hungry. And if you want to deploy it widely, you need to take care of these things, right? So currently it's very expensive to run these algorithms. There's not enough hardware. That's why NVIDIA's stock is in the several trillions. We need to work on both the, kind of like quality as well as the efficiency of these devices, of these algorithms. While this is happening, though, we also should think more deeply about how AI agents are going to interact with each other and with humans. As AIs are more widely deployed, they're bound to interact with each other and with humans. And to plan this agentic AI future, we definitely need to think about how an AI makes decisions when it's anticipating that those decisions are going to be impacting the decisions of other AIs in the same environment. So we would need to think about a blend of AI and game theory. And this is sort of like what I wanted to talk about today. I wanted to discuss where we are on this front. Of course, AI and game theory go back a long way. In fact, it goes back the interaction to the origin of these fields. In particular, the RAND Corporation, did a lot of research in both game theory and AI. So that one could say that the roots of both fields can be found there. I mean, of course, there was some developments in game theory before that, but a lot of the researchers working there were thinking about optimization, game theory, and AI at the same time. Of course, Alan Turing's famous imitation game paper is thinking about intelligence and how to distinguish it, how to distinguish artificial from natural human intelligence by setting up a game. And around the same time, researchers are starting to think about how to get algorithms to play games that humans excel at a human, or hopefully, they didn't achieve that, but like at a human or superhuman level. And the superhuman step was achieved several decades later, first with Kasparov versus Deep Blue by IBM, and more recently by AlphaGo, beating Lee Sedol in Go. And over the years, we have seen a lot of headline results where algorithms play difficult games at human or even superhuman level. And beyond games, we've seen a lot of settings where either implicitly or explicitly, a game is taking place. In the panels of this slide, you see on the upper left-hand side what I've talked about, which is games. On the right-hand side, we have applications that are explicitly multi-agent. So we have robots playing soccer. We have self-driving cars that are driving on the streets in the presence of other humans or other self-driving cars. We also have, the beginnings of using, AI to think about economic policy design. At the bottom, we have applications that are not explicitly, they're not born multi-agent, but thinking about them as multi-agent is fruitful. At the bottom left, the panel is talking about adversarial training. I'm going to get to that in a few slides, so let me not spend much time now. On the bottom right, I'm talking about alignment, right? So thinking about who the final users of models are and what objectives those users have, and thinking about how to train an AI system so that it serves all the subpopulation of users that are going to be using that system. So these are all applications that, one way or another involve different objectives. And they're fruitfully studied as multi-agent game theoretic systems. At the same time, we're not exactly ready to address sort of like situations like this. So there's a lot of challenges that remain on the both algorithmic and mathematical and modeling level. And I wanted to spend a little time thinking about those challenges. Through a set of examples. So in this video, you see a Waymo car that is trying to change lanes in some highway in California. But it's been antagonized by human drivers, so much so you see the self-driving car with the cameras on top. It's been antagonized by human drivers, so that so much so that it abandoned the attempt of entering the highway. It exits the highway and tries again. So we see here like a super advanced AI system that is unable to do something that humans, for the most part, do very well. Now, this interaction, the highway is a strategic interaction. Humans are pretty good at doing it. Because like humans are very good at processing signals that other drivers send them to understand whether it's a good idea to change lanes or not. AIs are not that good at the signaling game that takes place on the road. This is a much more trivial example. This is me asking GPT, probably until 01. 01 probably was the first iteration of GPT that fixed this. This is probably GPT-4. So I'm asking GPT-4 here to help me play tic-tac-toe. I tell it that I'm the X player and I'm about to play. What should I do? And GPT tells me to play at the end of the second row, which is obviously not the right strategy. Which is bizarre, right? Because these systems are really, they have read and processed, digested so much information from the internet that they have definitely seen versions of tic-tac-toe being played, like a lot of tic-tac-toe being played on the internet. Tic-tac-toe also is like a trivial game. It doesn't have like an extensive game tree. It's basically bound to end in a few moves. Despite the finiteness of the game and the fact that it's all over the internet, GPT cannot play it. That's bizarre. So the point of these two slides is that if you don't explicitly think about training your AI to be a good, a player, it's just not going to be strategic. It's not like being strategic is not going to be an emergent property of reading the internet. My second example is this adversarial attack problem that exists in essentially any AI system that we have trained in the past 15 years. So it is well understood that sort of like what's happening here is that like the picture on the left, if shown to a state-of-the-art image classifier, is recognized as a pig, as it should. On the other hand, the picture on the right is recognized as an airplane by the state-of-the-art model, even though in the human eye these images are essentially the same. The only difference between these two images is that what happened here is that I took the first image and added the second image to produce the third, except I didn't add the second image. I added like 5 in 1,000 times the second image, which basically is an insignificant addition to the first image. So that's why you cannot see any difference between the two images. Nevertheless, a deep neural network sees a lot of difference between the two images. The deep neural network is not robust in these types of noises. These are not, by the way, this is not IID noise. This is a noise that has been very well selected to attack the classifier. Point being that if the classifier is deployed in a setting with humans that want to fool a model to think that this is an airliner, then they can't do that. So all these systems are very easily attacked. They can be very easily manipulated by strategic agents. And robustifying them is definitely related to thinking about this strategic interaction that will take place once the classifier, in this case, is deployed in the real world. For my third example, I wanted to talk something about economics, closer to economics. This is a simulation done in the paper shown below at the bottom of the slide. So in this simulation, what the authors thought about is what happens if sellers, let's say sellers on Amazon, use algorithms to price their items. And the example these guys took was a symmetric duopoly. So you have two firms that sell the exact same good. So you have good competition here. And if these were humans, what economic theory thinks is going to happen is that the sellers selling the identical goods are going to converge to prices that are competitive. On the other hand, what the authors thought about is what happens if you have an AI algorithm that sets price for each agent. So each agent runs an independent Q-learning algorithm, like a type of reinforcement learning algorithm, to set the price of the item in the next round as a function of what has happened in the previous iteration. So like you think about like the seller changing the price of their good every day as a function of what has happened in the previous days. But rather than a human doing it, you think about what happens if an AI algorithm does it, and a particular one that is very common in these types of dynamic environments. And what they observed is that rather than sort of like the numbers don't matter, the picture matters. So rather than finding competitive prices for the goods, as economic theory would suggest, the algorithms converge to very high prices. In fact, prices that are closer to the collusive prices than to competitive prices. And it's also very interesting how the algorithms, what types of policies they arrive at to make sure that sort of like under the learned policies, these close to collusive prices are being sustained. In particular, in the learned policies, if you were to take one of the prices and push it down and then let the algorithms take over, there's an interesting dance where sort of like, if you push the price of one firm down and then let the algorithms take over, then you'll see the second firm sort of like pricing a little bit above, leading to sort of like a iterative process that, progressively increases prices in response to each other and eventually settles back to the close to being collusive price. So the point of this slide is if you're a policymaker you're trying to think about what will happen in your markets if you let algorithms take over, you have to be very alert about things that may happen that you weren't expecting to happen if humans were in the picture. But algorithms, iterative algorithms responding to the history and stuff are not humans. They're just mechanistic update rules that may settle and at some very interesting types of behaviors. So one has to be very alert when regulating markets in this brave new world that is about to, that is rising. My fourth point is more technical. It has to do with sort of like how we train these AI systems. So as you may know, there's one algorithm that trains AI systems these days, and it's gradient descent. So you start, you initialize the parameters of your model somewhere, and then you progressively improve the parameters by a little bit. And the optimization landscape is something very complicated, like you see on the left-hand side. And if you start someplace, you're going to arrive at some local optimum of your optimization problem, which would correspond to a pretty good AI system. But the point is, this algorithm is bound to arrive at a local optimum. Right, so you initialize it, you run, I don't know, Adam, you run Adagrad, whatever algorithm you want to run. You will eventually settle at some local optimum of your learning objective. Unfortunately, when there are more than one AI systems that you're training together in the same environment, so if I'm training my self-driving car while you're training your self-driving car, this algorithm doesn't work anymore. Gradient descent is not a good algorithm for multi-agent settings. In particular, it can be cyclic or chaotic in terms of its training dynamics. And it's really challenging to make it stable. So those of you who, for example, tried to train a GAN, like a generative adversarial network, you definitely would have, run into this issue. Like training GANs were trained as a min-max problem, so 2-agent zero-sum games. They were really, really hard to train because of this instability of gradient descent. And for this reason, or part of the reason was that they were replaced by diffusion models. So now, for the most part, people do diffusion models for generative models rather than GANs, and a big part of the reason is the fact that gradient descent is unstable. So the last thing I want to mention is that game theory also breaks. Not gradient descent is problematic, but also game theory breaks. And here's the reason why game theory breaks. So a common setting that you should be thinking about in this world is that sort of like You have, a lot of agents, a lot of AI agents in your environment. And every agent is like a very complicated system. Like, for example, it's a deep neural network. And what you're trying like this neural network, for example, could be mapping the state of the environment to the next action taken by the agent. And in particular, it's going to be a super complicated, non-convex function, and the starting space may be non-compact. Easily gets high dimensional, easily gets non-compact. Similarly, the player utilities are going to be complicated in a general setting like this. Many times you don't have explicit utility functions for the agents. You have simulators assigning utilities to every agent after doing a simulation. So in particular, these utilities are probably not going to be concave and might also not be differentiable. And this is not a setting where game theory thrives. Game theory likes to see compact utility functions and compact strategy spaces, and hopefully low-dimensional strategy spaces. When you have non-compactness, non-concavity, and high dimensionality, things break. And many of the standard notions of equilibrium fail to exist. And because they fail to exist, it's not even clear what optimization target one should be after in these settings. Game theory makes recommendations when certain conditions are met about the interaction, but those conditions go out the window the moment deep neural nets and high-dimensional strategy spaces are involved. So game theory doesn't have like a very clear suggestion for what we should be even after when we train a self-driving car to interact against another self-driving car, or a robot arm to interact with a human, and so on and so forth. These are not the multi-agent settings that game theory loves. So this is a summary of the challenges that we're facing. And to prepare ourselves for this brave new world of multiple interacting AIs, or AIs that are interacting with humans, we really need to expand our technology to prepare appropriately, right? And that involves many interesting challenges at both sort of like the algorithmic level and the mathematical level. So let me summarize sort of like the lines of work that I think are valuable on this front. It's not an exhaustive list, but I try to compress some interesting directions on this slide. The first one is, at the mathematical level, you want to expand the foundations of game theory to be able to give recommendations of what ought to happen, or what is an interesting thing to do when the standard assumptions of game theory break. Like when you have non-concave utilities and non-compact strategy spaces. It is very important in practice. I mean, if you see a lot of the developments that have happened on the multi-agent learning front in the past decade, like, let's say, Go and poker and this and that. Like, if you think about all of them, one thing that you have simulators of the game. And having a simulator of the multi-agent environment that you want to solve is really crucial, because it allows you to go through the design loop of your algorithm very fast. More broadly, I think it is very fruitful to develop simulators for your multi-agent interaction of interest. Without simulators, you would have to test your strategies in that environment and iterate after collecting more data, but that's obviously a time-consuming approach. In a future where my AI agent is interacting with your AI agent, negotiating against each other or whatever, it's very important to ask how much a more sophisticated agent can exploit a less sophisticated agent, right? I mean, exploitation happens between humans, but in a world where sort of like different nations or different individuals have different levels of quality of solutions, of algorithmic, of AI solutions, it is important to think about how sophisticated agents might exploit other ones, and if you're a regulator, intervene so that you don't have excessive unfairness in your economy or society. Finally, I think a lot of the strategic interactions are intermediated by natural language, and I think there is a lot of interesting research directions related to that. So I think there is super interesting problems related to how to develop good strategies that use language as a medium of strategy, like in negotiations or in law applications. Similarly, developing algorithms that can do strategy over code. Code is also, I mean, it's not natural language, but it is, language. And designing strategies over over the code space is a super interesting thing to do. Obviously, you might want to combine different data modalities like language and images and other high-dimensional, non-structured data modalities that are not typically studied in game theory. As I've already touched upon, it's important to train models to care for different stakeholders. And perhaps I want to close with an application like that. Use a collaborative human and AI framework to help elucidate, human interactions, right? So this is sort of like using technology not to address a technological world, but using technology to understand a human interaction. So I had this slide that I want to skip. It was more a technical slide because I want to get back to I want to get to the sort of like this in the last few minutes I have this direction that I actually find super interesting. Which has to do with thinking about strategic settings where natural language or other data modality plays or can play a critical role. In the following sense, as input or output of the strategy. For example, in many games include chip talk. A negotiation involves chip talk, and like other games like Mafia or Diplomacy or Werewolf. All of these games involve chip talk as part of the game. Having AIs do that chip talk in an effective way, either for like playing games or for negotiating over language. Sort of like combining natural language as a signaling mechanism and conditioning on signals to choose strategies is a super interesting thing to do. So, right, so, it's important to study games where language is a part of the game, is as input or output or as a signal. Generative AI can also be used to increase the efficiency of an interaction or an institution in the following, in various ways. But here's an example from a sort of like some recent work that I did with my postdoc Yannis Daras and several undergrads. What we thought in this paper is using generative AI in online auctions, and in particular in selling banner ads. So typically banner ads are sold to the highest bidder, right? So there is whenever there is an opportunity for selling a banner ad, there is the auction, the auction environment decides a small number of eligible advertisers that bid to get the banner ad, and the winner of this auction that runs in milliseconds is given the ad opportunity, and they show their banner on some internet page. So what we thought about in this work is to say, look, like traditionally, there's a single winner of the banner ad, right? But Gen AI allows us to do more interesting stuff. So for example, why not give the banner ad to two winners or more to increase the efficiency of the market? And here's an example of the stuff you can do, right? So here's just a simulation for the paper where sort of like Gatorade, this drink, or North Face, the backpack or whatever, the clothes company, bid to win a particular banner ad on the internet. And in these different panels, we show the different mixtures of Gatorade and North Face you can get by invoking a generative model. So in this market, agents don't come with sort of like just their bids, but they come with a diffusion model, like a generative model, and as well as a scoring function that says, the diffusion model says, here are the images that I would like to show in this banner ad, and the scoring function says, here's how aligned the particular image would be to, my desired images, right? And your auction can take this information, and as well as the bid of every agent, and decide on an allocation that does not have to be 1-0 or 0-1, right? So like, you don't need to only show a Gatorade bottle with a hiker or a North Face backpack with a hiker, but you can do intermediate images where, to different extents, you show, both of the advertisers winning the auction, right? So you have combined outcomes. And those combined outcomes that are enabled by Gen AI can increase the efficiency of your market. This wouldn't have been possible in the past, right? In the past, you can't fuse images on the spot, right? You cannot produce new images on the spot to show in the banner. So traditional banner auctions were restricted to either one of the bidders getting the banner. But Gen AI allows you to do a lot more stuff, and I think it's just an example of the cool stuff you may want to be doing there. The last point in this list, and sort of like an application that I would like to discuss a little bit more, is using natural language to understand, to collaborate with humans to produce models of real-world interactions. And in the paper that I want to show just a couple slides on, because I think I'm getting out of time, I'm already out of time. How much time do I have left? I cannot hear you, but I
5 to 10 minutes.
assume
5 to 10 minutes yet?
Say again?
5 to 10 minutes yet?
Okay, perfect. Okay, yes. So, the last thing I want to show is as an example of sort of like human AI collaborations to understand human interactions is this recent paper with Christos Paparimitriou and several other collaborators from Google DeepMind. Is using a human AI collaboration to understand stories. And in this paper, we looked at Romeo and Juliet. So, this application is not about, using AI to, to train AI agents to play interesting games. It's more about using the power of AI to understand natural language to help us understand human interactions, and in this particular case, Romeo and Juliet interaction. Why did we want to use game theory to understand Romeo and Juliet? Well, because we wanted to build a model of the dilemmas that these characters face in Shakespeare's play. And the rewards they would receive depending on different outcomes. And also, once we have a model of like what dilemmas they face and what like counterfactual rewards they would have taken in different outcomes, to understand what are optimal choices they could have made, and to think about that, to understand how tragic the story is if like sort of like the story didn't go according to the plan. Yeah. So there is a line of work for, I mean, of course, we're very small to analyze Shakespeare, but there has been a line of work using analytical techniques to study stories in fiction and theater, and that line of work basically plots the rise and the fall of characters' fortunes or other statistics about the interaction of the characters along the plot line, right? So like as the narration takes place, they graph kind of like how happy characters are, the interactions of the characters, the use of certain words with certain color as the narration, progresses. But what we think is that sort of like when you're analyzing a play or a story, it's also important to think about the paths that were not followed, like what makes the choices of a character tragic are sort of has to do with the paths that were not taken. Right? You cannot. We thought that you cannot understand a story but just following the plot line. But you should be thinking about like all feasible plot lines and how the choices that characters made, as well as the choices that were made by fortune, sort of like selected one path out of the many paths. Perhaps that path doesn't look that nice, and this is what makes a story unpredictable or like tragic and stuff like that. So we wanted to think about the whole tree of storylines, and compare that to the story that like Shakespeare chose to narrate as a means to understand how interesting the story is and sort of like how tragic the characters are and stuff like that. Why did we want to use LLMs? And by the way, game theory is the way to study, decisions and how decisions affect the fortune of the players, and thinking about counterfactuals and stuff like that. Why do we want to use LLMs? Well, because, like the story is written in natural language, and um, we wanted to use the LLM to extract data from the play. We didn't want to read the play. I mean, we have read the play in the past, but didn't want to read it again. About the dilemmas that agents face. But also we wanted to use LLMs for another reason. LLMs have a lot of world knowledge about, sort of like the era in which the play was written. So they can be very useful in modeling the situation at hand because they have some knowledge about the time of the play and stuff like that. Long story short, what we did is we asked Gemini a bunch of questions like this. In Romeo and Juliet, Romeo is banished from avenging Mercutio's death and killing Tybalt. Juliet's family intends for her to marry Paris, not the Paris from your conference, but a different one. Friar Lawrence has other ideas. Name options that Juliet could consider, including ones that her family might prefer, other ones that may appear more risky, and ones that may appear tragic to the audience. Please list a few options, okay? And then, like Gemini helps us sort of like proposes some things to us. Maybe we like them, maybe we don't like them. We interact with Gemini. In any event, we basically, by asking questions of this form, we can plot a tree of options that characters have available to them under different ways the story can progress. The other thing we can use Gemini for is, as I was alluding to earlier, is to use its world knowledge to assign probability for different events. So, for example, we can ask Gemini questions like this. In the case where Juliet chooses to fake her own death, what's the probability that her message alerting Romeo to this plan reaches him in time? And Gemini, cooks up a number, in this case 30%, and then but it provides some arguments for why this number is reasonable, and the justification that I haven't included here. You can see it in the paper. Talks about the technology of the time and this and that, how messages are transferred. So we get a number there. Of course, we have to eventually jiggle whatever model we produce. We have to jiggle it around these numbers because these numbers are just fake numbers. But we have to see eventually the robustness of the model. But we get a in this collaborative fashion. We can basically plan. We can get a model of the interaction. And long story short, we can build a tree that basically plots. We can, and it was not very hard. It was pretty fast to build this tree, right? So we can build a tree of like sort of like all the places where like either Romeo in blue or Juliet in red, or nature, which is the dice. Makes a choice. And in particular, in trying to understand sort of like Romeo and Juliet, we actually thought about two possible game trees. And I want you to pay attention first to the, on the right of this boundary here. This is the first game that we thought about, that we built together with Gemini. This game is sort of like assuming that essentially all the characters are fully rational, like Juliet and Romeo are fully rational. And in particular, Juliet, ignore the numbers here. So Juliet, starts the game by either deciding to marry Paris, or to commit real suicide, or to fake her death. And sort of like, like if she does marry Paris and Romeo hears about it, then, he has to decide whether to accept its fate or keep fighting for Juliet. And, like these nodes assign different payoffs to Juliet and Romeo. If so some interesting stuff happened at the bottom side of this tree, because if Juliet fakes her death, right, the news of her death spread, but so Romeo, may or may not, like if she fakes her death, and sends a secret message to Romeo, the message may arrive to Romeo, or might be lost. And of course, if the message arrives to Romeo, Romeo is not going to commit suicide. But if it's lost, he may ponder, committing suicide as well. At which point, Juliet would also commit suicide. But sort of like, and if she commits real death, then real suicide, Juliet in the beginning of the game, then again the news will travel to Romeo, and Romeo will again decide whether to also commit suicide or not. But the point being that, like, sort of like, if you look at the bottom tree, this tree here, there's a unique strategy for both characters, right? So there is a unique optimal strategy for Juliet to fake her death, which basically means that regardless of whether her message arrives to Romeo or not, it's in the best interest of Romeo to not commit suicide, because again, there's an optimal strategy for Juliet not to commit suicide, but to fake her death. So if, in this sort of like game, things are pretty straightforward, and it's not rational for Romeo to commit suicide.
So,
on the other hand, sort of like...
Konstantinos, I will have to press a bit, so because there are people who would like to interact with you, not in the world of interacting AIs.
Yes, just 1 minute and I'm done. So what we found here is sort of like is that the only way to make sense of Romeo and Juliet is to include a first node where Juliet is not being rational. If Juliet is not being rational and might be overwhelmed by grief, and there is a chance for her to commit suicide without rationally thinking about the interaction, then when the message of her death reaches Romeo, Romeo now is not able to distinguish whether the death is real or not real, and this is what sort of like makes the story interesting. So long story short, by using Gemini to help us build a model of this interaction, we are able to sort of like write down two games. One game is not super interesting. The fortunes of the players are very predictable because the strategies in this game are very deterministic. So nothing interesting happens, nothing is really tragic. The only way for the situation to become tragic is, leaving the possibility that Juliet cannot rationally think about the interaction in the beginning of the play and just goes and commits suicide without thinking about the strategies. So this, which gives rise to interesting sort of like fortunes going up and down and having a lot of variance in the story that Shakespeare narrates. This is what I had to say, and this was an example of human-AI collaboration to think about strategy. Thank you very much.
Thank you very much. So it was a very, very, very passionate talk, and really, today most AI is everywhere, and most people tend to think AI as to have a tremendous trust to AI, even more trust than people sometimes, and to be able to see the limits of a world of interacting AI is really challenging. And thank you for setting this framework for the discussion, as well as for further research. So there are many participants in the room who would like to ask a question first about. So I will directly give the floor, and be a good president. Don't have the temptation to ask more questions myself, but so yes.
Thank you very much for your talk. It was great, and it's an honor to have you here, even online. My question is, do you think that our goal to train AI to handle multi-agent settings also implies them adopting human-like features like ego or irrationality? And if yes, does this concern you?
Not directly, for the reason that you know, like one way or another, to train an agent, you have, you have to give the agent, you have to endow the agent with certain utility or utility functions that they want to optimize, or at the very least, you know, imitate human agents, which in and of itself is an objective function. So, like, the way we know how to train agents is to change them in a way that optimizes an objective or a trade-off among objectives. So it's hard to think about how to train them without giving them objectives. And the moment you give them objectives, you can call that, I guess, you can call it ego. But I agree with you. Like, how to choose those objectives is very important. And in a multi-agent interaction, there are, in fact, that means there's also a lot of opportunities to make the world better. When you design a self-driving car, you can endow it with the utility function that it has to optimize it has to minimize the driving time from the beginning of the trip to the end of the trip, right? But you can also give it some altruistic utility that sort of like it has to be a better driver on the roads and, send information about traffic to other cars and this and that. So, and that is an opportunity. So I agree with you that badly designed utilities can lead to a very strategic, world where everybody is for themselves and, optimizing, like the utility for the owner of the AI. Or you can get to a world where AIs are better behaved because you explicitly ask them to do so in their utility function. And maybe that, can save humans from, perhaps their instincts of, not being collaborative in certain scenarios. So it can go either way. But I think it's important that we have the ability to design the objectives in a quantitative manner, and perhaps add altruistic motives to the agents.
Thank you very much.
Next one. Thank you very much. So yes, in the middle.
Hello, thank you very much. So if we have an example where the AI agent interacts with human players, what I would assume is that the human player, knowing that the other player is an AI agent, would change his reactions and his moves to this AI agent. So this wouldn't make it harder to make a predictable model that, assuming that the human player's behavior changes.
Yeah, and that's exactly the point of game theory, right? Like, first of all, like what you said is exactly the reason why this Waymo car that I showed you cannot change lanes, or at least one of the reasons. And I've seen it happen, when I drive in San Francisco. When where you are next to a Waymo, you know that the Waymo car is made very conservative. So then as a human, you want to exploit that, right? You can go right in front of the Waymo car. You know it's going to brake or whatever, right? So like, and for this reason, to train the Waymo car appropriately, you have to take into account, you have to anticipate how other agents will respond to your strategy. So this is exactly what game theory is about, like anticipating the impact of your policy to the other agents' policies, and so on and so forth, until a fixed point where everybody's policies are optimal against each other.
So thank you very, very much. We have passed a bit our time, and we are off schedule, but it was passionate listening to you. Unfortunately, we don't have time for more questions. Thank you again, Konstantinos, for being with us.
Thank you very much. Thank you for your attention.
It's been an honor for us to have you, and looking forward to meet you again.